So the 3.2 section, they entitle basic derivative rules and rates of change, right? But I'm going to call it shortcuts or derivative shortcuts. Now, in our class yesterday, we talked about, first of all, the derivative equals the slope of the tangent line, right? Or even the slope of the graph if it is linear, right? Does that make sense? We also discussed that the derivative equals another thing. Does anybody remember what it was?
Instantaneous rate of change.
Instantaneous rate of change of the function, right? That is the slope of the tangent line as well, right? But the instantaneous rate of change could be another way they would be asking you for the derivative at x equals whatever, right? F prime of A. Now, we talked about there's an average rate of change also that always goes between 2 points, right? Rate of, right in there should be change of the function. Of, thank you. Of. So tired. Anyway, so that's the instantaneous rate of change of the function at a single number. And many times they won't even use the word instantaneous. They'll say, what's the rate of change at x equals 2? It's one x value. That's a derivative. Find it. Use one of these shortcuts and be happy with yourself. But let's just use the terminology that's on the calculator. This also means derivative, right? And Tony told us the derivative of any constant has got to just be what? It's got to be. We did it in our examples. We showed that the slope of every point on a flat line is 0, right? So the derivative, this is a shortcut. If you ever see a constant, like 10, or what's the derivative with respect to x of pi? 0. Pi is just a number, right? All right, the derivative with respect to x, though, of a x to a certain power. This is where I want us to look. It'd be nicer if I had my old notes. Anybody have their notes from last class?
I do.
Are they neat enough for us to read?
Yeah, it's got it.
You tore it out for me? Bless your heart. All right, so let's look at some of the derivatives we found. All right, these were the alternative definitions, right? Oh, so we did do one.
Yeah, I was trying to say that.
We did do one example, didn't we? So our function here is x squared plus 1. What is the final derivative? So just take a look at those. Fully embrace that. We went through all the steps. There it was, 2x. Here is the function x cubed plus 2x. Its derivative is 3x squared plus 2. Just looking at those two examples. the derivative of x squared plus 1 was 2x. The derivative of x cubed plus 2x was 3x squared plus 2. Any relationship jumping out? The power becomes the coefficient, and then what happens to the power? It goes down one. Is that a good hypothesis here? The power comes down. And by the way, we have a plus 1, but we did already talk about the derivative of a constant is just what? So like we could have said plus 0, but no need, right? Did we do any more examples that was your homework? But here's one. X squared plus x minus 3. 2x plus what? 1. Is that the same power rule? Power comes down as 1. Lower the power by 1, what do we get? X to the 0, so it goes away. On this one, what do we get? 3x squared minus, I think we've just come up with our rule, haven't we? What's the derivative of x to the n? N, x to the n minus 1. As this is called the power rule, and that will be going through your head 100 times between now and December, you know. When I take a derivative, my mantra is power down in front, lower the power by 1. The constant multiple rule is this. The constant multiple rule says if I have a constant multiplied by a function, then I can just take that constant out and kind of not deal with it, and then take the derivative of the function. That's called the constant multiple rule. Uh-huh. Well, there's also, well, you will use it, but it will be kind of second nature, okay? If we have addition or subtraction, we just simply add or subtract all the derivatives. And that was kind of like understood in what we just did here. So the thing is, we're just going to subtract. When we take our derivative, y prime, right? This, we're just going to take the derivative of the first term and subtract it from 2, right? But, well, we're going to just do these two individual derivatives. What do we think? What's the thought process? Power down. But see, that is a constant multiple. Just multiply the 4 times the 3, right? 12. X, lower the power by 1. 1 times negative 2 is negative 2. X to the 0, right? Adding and subtracting.
Is that what we just did at the bottom, the add subtract?
Yes. Adding and subtracting is what we, you know.
Okay.
This is applying kind of both of these rules. Because the constant multiple, but honestly, the constant multiple is like second nature, because when you power down in front, you're going to multiply it by the 3, right? That 3 stays there, right? 3 times 4, 12. Lower the power by 1. Power down, lower the power. Now, addition and subtraction work beautifully. This does It is not true. It does not work for multiplication and division. They have their own rules that we'll wait a second to go over. That they have their own chapter. Actually, it's 3.3, own section of the chapter, product and quotient rules. But they make things bigger, okay? But I would like us to look at, and that's pretty much it. We're looking at, oh, I lied. We got a few little like standalone trig rules, derivative of sine of x, derivative of cosine of x, the derivative of e to the x. And many times, like I've had kids that would make me prove the rules and why they work. And remember that the f of x plus h minus f of x? I can't make it cancel out the h's. I can't make it get the zeros gone. So, like, I have to use a rule that uses derivatives to do it. So how can I use the rule for derivatives to prove it just doesn't make sense? Yeah, but derivative of tangent is secant squared. We're not going to use it yet. So today's work only does sines, cosines, and e to the x's. There's a whole, if you go to the front of your book, there's like 20-some 36 derivative rules. But we never do the hyperbolic functions, and we will add on to these just slowly, okay? We won't learn all 30, at once. But the best I can do to show you what the derivative of sine is to draw a sine curve. Because didn't we practice that just on those few problems, like where we were sketching the derivative graph? Practice drawing your sine curves, because those help us to remember our special angles anyway, right? What is the graph of y equals sine of x? Starts off at 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, back to 0, right? Everybody good with that? So now, if we're going to plot points for the derivative, what is the slope of the tangent line? If I just kind of use my pen, what does that look like? It is the slope of 1. I'm going to plot that point. It's still positive, but it's a little less than 1, isn't it? 1/2 maybe. Until we get to what at pi over 2? 0. So we go down and we hit at pi over 2, we're hitting 0. What are all the slopes over on the left side? -1/2 maybe.
I'm so confused. Like, what are we doing? Like, what are you doing?
On this graph, we were checking out, this was the y, this was the function, right? And we were graphing its derivative. The derivative is the slope of all the lines, right? The slope of all the ones on the right side of 0 were +1, right? The slopes on the left side of 0 were all -1. This was drawing the slopes of always +1 and always -1. But there was another graph on there. Oh, there's my typical graph. What's the slope of the tangent line right here? 0. What's the slope of the tangent line right there? Also 0. So I'm plotting these points. On the right side of 0, what do you see the slopes doing? They're going up. increasing. On the left side, all of them are negative. Does that look like it's the steepest negative slope? Maybe -5, I don't know. And then it starts coming up because it's still negative, but it's flatter. This is what I'm doing. All of those are positives, just really steep positives. It's just plotting slopes of tangent lines at random points. We always read, right? What was that slope? Positive or negative? Positive, 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 positive. Yeah. I'm trying, I'm getting there, I promise, I'm getting there. So, everybody with me now? I'm seeing a slope of 0. I plotted 0, right? What are we doing to the right side? We're going negatives. The steepest negative looks to me like it's negative what right there? Negative 45 degrees, which is -1. And then we're still negative, but we're less negative. So we're coming up until we get this point where the 0 occurs. Over here, we had hit a negative, and so I'm just connecting all those collections of points. And somebody tell me what the derivative of sine of x is? Cosine of x. Woo! Yes. Woo-hoo. Yeah. All right. So the next one, I'm trying to find a different color. Purple's still too similar. Anybody got a different color other than blues? Oh, looky here, I've got a whole box. All right, found one. Let's do red. And let's look at the derivative of this cosine. Well, looky up there, the slope right there is what?
0.
So far it's on the sine curve, isn't it?
Yes.
But what do we do on the right side? What are those slopes, positive or negative? Negative until we hit here, probably -1. Still negative, but they're less negative, right? Until we hit what? 0. We are +1 right there. Still positive. What is this? We're +1 right there. Anybody want to take a stab? It's not regular sine of x, is it? It's the opposite. It's a flip over the x-axis.
Negative.
Negative sine of x. And again, just like the sines and cosines, I've tried to prove these people. I get caught every time. There is a proof in the book. I don't know where their magic comes from. But I think I can visually at least kind of show you. What does e to the x look like? Exponential. E to the 0 is 1. E to the first. Anybody know what e is? 71828. Nice. 1 over 2.71828 is something almost a third, right? A little over a third. So there's our e to the x. What does the slope of the tangent line look like right there at 0? One. Plot the point 1. What does the slope look like over here at 1? 71828, I bet. What about here? 1/2-ish, 1/3-ish? maybe 1 over 2.71828. So it turns out that the derivative of e to the x is just itself. That is crazy. Or as my daughter says, crazy. It's crazy, Mom. Yeah. So we have these formulas, mix and match, addition, subtraction, they all work. Now, where we get into a little bit of trouble is, now, we've talked about find the derivative. We know we're taking the derivative, right? Find the instantaneous rate of change. There's another word you might see, differentiate. That simply means find the derivative, all right? So if y equals the square root of x, I'm just jumping to not so easy. What we need to do is we need to rewrite it as x to the what? It's not negative. Negative sends it to the denominator. A negative, it is the 1/2 power. Yeah. You were on the right track, but the square root is the 1/2 power. The cubed root is what?
1/3.
The 1/3 power. Rewriting.
Oh, yeah.
Then we're going to use the power rule. What's the power rule? Power down in front. Lower the power by 1. What is 1/2 minus 1?
1/2.
Negative 1/2.
You don't 1/2.
1/2 minus 1 is negative 1/2.
1/2 minus 1 whole, which is 2 halves. 1/2 minus 2 halves, negative 1/2. Now, in general, if I start out with a radical, I'm going to go ahead and end up, what does a negative power take it? On the bottom.
I'm confused.
Power down in front.
But I thought that got rid of, like, I thought there wasn't anything else on the top.
No, the rule says power down in front. What does the power change to? Minus 1. So if we have fractional exponents and negative exponents, they keep getting more negative. A negative power makes it 1/2 times 1 over x to the 1/2, right? And the x to the 1/2 is the square root of x.
Okay, another example.
Here we go. The cubed root of x, I've already rewritten it. What is that derivative?
X to 1/3.
The derivative is power down in front, lower the power by 1. Are you seeing x to the negative 2/3? Or 1 over 3 times the cubed root of x squared? Hey, I'll accept this answer. I'll be fine with that, okay? But I'm telling you, you gotta know the radical form too, if there was a multiple choice.
I got the denominator.
Yeah.
I've seen it for like the first one, so I did it, but I don't understand the 1, 3, and then x squared times it.
The bottom number is the root,
Okay.
is the index for the root. The top number, guys, this is a valid way to write it. Another valid way to write it could have been 1 over 3, the cubed root of x, and then squared it. These two are equal.
If the 2/3 was positive, would it be on the top?
It would, if the 2/3 was positive, it would be on the top, yes. Yeah, those, see, See, this is why I've spent a lot of time in pre-calc this year on these radicals. Y'all, I should have done it with y'all last year, sorry.
I remember this.
You do?
Yeah.
Okay. Oh, there was one I wanted to pick on. It was this problem right here. Let's do it using our new rules. Yeah.
Can you go back to the differentiate? I want to do this.
You wanna what? Oh, okay. Well, you wanna just take a picture of the whole page? You wanna come up? Are you-
Just the differentiate part.
Oh, okay. Since I am putting them on YouTube, I probably should be writing neater. I'm sorry. Let me write this example in beautiful form. F of x equals x plus 4 over x. And we want to find the equation of the tangent line at 4, 5. I'm just jumping and still doing more applications. Guys, if we have a fraction, we got to look at it carefully. If we have radicals, we've got to look at it carefully. So a rewrite is always warranted in this case. By the way, notice my math language. I'm keeping f of x. I'm showing myself I have not taken the derivative yet. How do I rewrite 4 over x? 4 times x negative 1 power. Everybody follow that?
So like, you just have to like.
You have to understand if it's in the denominator, it's a negative exponent.
So like, why doesn't the other x get anything?
Because it's
Not in fraction.
It's already to the first. It's not a fraction. It's just itself.
Yeah.
So somebody tell me the derivative now. We could even add to our rules if you really wanted to. Under the derivative of c is 0. The derivative of x is going to be what?
X.
1. We could add that. So the derivative of x to the first is 1. But if we do the power rule, power down in front, lower the power by 1, it still gives us x to the 0. So it's okay. Now what are we doing for this one?
Negative 4
X to the,
to the 0.
subtract 1 from the power,
Two.
which is the same as 1 minus 4 over x squared, correct? And look, when I split this up before, it did give us 1 minus 4 over x squared, didn't it? But with a whole lot less mess. All right. So now we have the derivative, and we can just take one more step to figure out what's f prime of 4, the x value. 1 minus 4 over, what's 4 squared? Or 1/4. What's 1 minus 1/4? 3/4. Which, by the way, we already did. Y minus y1, slope, x minus x1. If I'm looking for the slope of the tangent at a specific value, I simply plug in that x value.
Maybe you bring that 1 down.
Wait, if you're plugging in, are you plugging in 4 for x?
Yeah,
Wait, my
the 1 stays 1.
4 for x.
x squared. 4 squared is 16. I'm replacing that x with a 4.
Okay, let's put it into that.
This is to give me the slope of the tangent, right?
Sorry, I was looking at the first
Yeah, if you plugged it into the original, it would have given you the 5, right?
Yeah.
All right, so let me make sure I've gotten, let me just mix them up. G of x equals 3 cosine of x minus 2 e to the x plus 1 over x squared. Think of us trying to do that long derivative formula with this one.
I just wouldn't.
That's your division.
The derivative of cosine of x, look at your table, look at your, negative sine x times 3 would be negative 3 sine of x, right? What was the derivative of e to the x? The same, keep the negative 2 in front of it. So, sorry, this really wasn't that hard, was it? This, I probably shouldn't have started my derivative. How should I rewrite 1 over x squared?
X, no, 2x to the,
What's the power, what is this equal to? X to the negative 2 power. Now we're going to take the derivative, negative 2 power down in front. X to what power now?
Oh, negative 3.
Negative 3.
There we go.
Now, I would absolutely accept this answer, but understand, many times they won't write a negative, like if it's multiple choice.
That's the, what is MC?
Multiple choice, free response.
So that answer is the derivative.
That answer is the derivative. And how long did it take us? Even, this one took us a little bit to chalk through the negative exponents, okay? But compared to the long derivative formulas, you know. I got a few more just for the nuances. I'm just gonna put them all down here. 5 over 2x cubed minus 5 over 2x squared plus 7 over 3x to the negative 2 down there.
you just want to.
This is one example that really could have been and should have been 4 examples, but it's okay.
More efficiency.
Wait.
We got to rewrite every single one of them anyway, so let's just rewrite one big Y. Here's a nuance that people have trouble every year. This is multiplication. What I want you to understand is this can be rewritten as 5 halves x to some power. Negative 3 power. So everybody good. I can pull out, remember that constant multiple rule? I can pull out the 2 part and I can pull out the 5 part. Is it the same for the rest of them? This one is a whole 2x that's being squared. I really need to rewrite this one twice. That's the same as 5 over what? What's 2x quantity squared?
4x.
4x squared. So really, I'm gonna say this is minus 5 over what? 4x to the negative 2. Oh, this one was just trickery. 7 over x to the negative 3 that's on the bottom. Where does that x to the negative 3 go? I mean, x to the negative 2. It actually just goes as a positive 2, doesn't it? On the top. So this is just 7/3 x squared, right? This one has the 3 also going to the negative 2 on the bottom. 3 squared is, times the 7 would be 63 x to the,
Wait, why are you timesing it by the 7 if it's on the bottom?
let's write a thought cloud here. We have a thought cloud coming
Would
up.
it not be 7, 9?
I know I'm right, just give me a second. I'm not finished, but give me a second. 3x to the negative 2 grouped. That is saying 1 over 3x squared, correct? What is 3x squared?
9x.
9x squared. And I leave the 7 over 1, change division to multiplication, 9x squared over 1. Whoa, that happens to be what? 63x squared.
Well, why didn't that happen with the other one?
Because now parentheses.
Can I see that picture? Yeah, parentheses. This one, can I see that thought?
My thought cloud. I'm sorry, my thought bubble right here.
There's no way I can do this for myself.
Oh my goodness. If you got a negative exponent in the bottom multiplied, take it to the top. That's all there is to it. As long as it is multiplied, you can just throw them in the numerator. As long as there's no addition. Addition causes issues. Then you're going to be pulling out a fancy form of 1 and you're going to get over it. All right. Said with the utmost love, of course. Now, take the derivative. All of that was just a rewrite. See, I showed I hadn't taken the derivative yet. What are we doing? Power down. What's negative 3 times 5 over 2?
Negative 15.
Nice. Look at you fractioning. Lower the power by 1 becomes
Negative 4.
nice. Power down. Oh, minus times a negative would be a plus. All right, we got a 2. 5 over 2. X to the what? Negative 3. Power down in front again. 14 over 3. X to the first. Yep. Power down. Oh my goodness. Minus 126x. Oh, we got common factors. That was me putting too many together, wasn't it? But we did start out as fractions, people. While this would work in a free response world, believe me, they're not all free response questions, so we do need to understand that x to the 4th could be in the bottom, correct? With the 2. The x cubed could also be in the bottom with the 2. We could put the x on top with a 14 if we wanted to.
Aren't you just going back to
Oh,
where you started?
actually, no, no. These are both common, so we got to get a common denominator. 3 times 6 is 18, 7, 378. Negative 378, positive 14 would be minus 364, and the plain x over 3. That is a beautiful fraction. I'm pretty sure I have stretched you on that one. use the rules of differentiation to find the derivative. What if I ask you to find the slope at a given point?
Plug in the X.
Put it in the calculator. Desmos.
Repeat after me. Desmos makes us. Desmos makes us dumb. All right. The directions here, while we could say write the equation of the tangent line, I think they just say find the slope of the graph at the given point. What are we actually finding? The slope of the graph is the same as the derivative. So first of all, we're just going to take the derivative, right? What did we say the derivative of cosine of x was?
Negative sine X.
And negative times negative would be positive 2. Oh, t, sorry. And the derivative of 3 is just 0. That's beautiful. So now we're just finding g prime of pi, right? Oh, does anybody remember what the sine of pi is?
Sine of pi is, that's 0.
It is 0 because sine starts off at 0. Pi over 2, it hits 1. At pi, it's back to 0. So just for funsies, if I said write the equation of the tangent line, what would you say? 7 equals 0 times anything. That's just y equals 7, isn't it? That was your bonus. So, the only other thing I've not gone over, I'm sorry. H of x. What did I say at the very beginning when we added those rules in? We said we can do addition and subtraction all day long, but what can we not do?
Multiplication and
Division, multiplication or division. So we have to rewrite.
Wait, so what is this in?
Still finding the derivative. Still finding the derivative. But we don't have the quotient rule yet. We can still do this problem because there's a single term in the bottom. Does everyone understand this could be rewritten like this?
Yes. Oh, yeah.
So what is it really rewritten as? X. 6 over x squared. We got to rewrite that as 6x to the... Nice. It's not that hard, is it? What's the derivative?
That's
1. Power down would make it negative 6 times negative 2 would be positive 12. X to the,
-3.
yeah. And the only thing I would go back to is write it as 12 over x cubed. Now, I'm not going to get a common denominator and put them back together. But understand, that could be a multiple choice answer. They could make you do x cubed over x cubed plus 12 over x cubed. That could be one of their answers. Yeah.
I'm confused, so like the second H of x, like the x minus.
I took this x cubed and put it over x squared. Minus sign 6 over x squared. And x squared cancels out with 2 of those to leave 1.
Okay, I see.
6 over x squared is 6x to the negative 2. And then let's go ahead and do a multiplication one while we're at it.
Miss Washington, I have a feeling you're gonna something.
Well, tough. I'm sorry. Kind of, not really.
I thought you up a little.
Do what? You still, you mean down?
What?
This is up,
Oh, yes, down.
okay.
I just looked
Y'all must just be slow writers. I like
I'm just mentally slow.
I'm sorry.
Process.
Processing is fine, I understand. All right, guys, we have the same issue. This one's multiplication though, right? So what should we do? What should we do? I heard someone say distribute, but I'm gonna change that square root of x to be x to the what?
J.
1/2.
I'm still rewriting j, and I am going to distribute, like someone so astutely said. What do I do with those powers if I'm multiplying the like bases? Yeah, 2 plus a half.
3/2.
1 plus a half is 3/2. 2 plus a half,
5/2.
5/2. Good. Minus what?
3.
X regular squared, right? Everybody good there?
You just add the.
If you remember, multiply 2 times 2 is 4, plus 1 makes 5. Or you could say 2 is the same as 4/2. 4/2 plus 1/2 is 5/2. We haven't differentiated yet, people. Let's do it. What is it? Power down. Lower the power by 1 minus 2 2's would be 3 2's, 3/2. Power down 6, x to the first. And I believe we can stick a fork in this lesson.
Yay.